Hi, this is Gary Rubenstein, and the purpose of this video is to show you how to algebraically solve cubic and quartic equations. And we're going to build to this. I'm just going to write down a few questions that we're going to tackle in this video. First, we're going to review quadratic equations. Something like this. These look like strange numbers to use, but you'll see why we use those, where these are going to come up in some kind of context. Quadratic formula. Well, people knew how to solve quadratic equations back in like 1600 BC. The Babylonians would solve quadratic equations. And the quadratic formula is one way of solving quadratic equations, and that was essentially around for thousands of years. But the being able to solve cubic equations, well, that didn't happen until much later. A cubic equation like this, that has no x squared term, that was first solved around 1515 in Italy. Quadratic equation, I'll just place it around 1600 BC. Now, a cubic equation that has a square term, like x cubed plus 15x squared plus 360x minus 450. Equations like that were first solved 30 years later in 1545, also in Italy, in a very famous book called Ars Magna, written by Cardano. And in that same book, Cardano explains that his student, whose name is Ferrari, figured out how to solve fourth degree equations such as this one. So it's also 1545. Same book, but Cardano gives credit to Ferrari. So think about this. There was almost a 3,000-year period between the time that people figured out quadratic equations to being able to solve cubic equations. And in the same year, they also figured out how to do fourth degree equations. And I'm going to take you through this by doing a series of questions. And the video is going to take at least an hour. It could be even 90 minutes. We'll see what it takes. Okay, I'm going to start with the refresher of quadratic equations. A quadratic equation, some quadratic equations can be so-called factored, and this is an example of one. Most quadratic equations cannot be factored. But if you can factor it, you look for two numbers whose product is positive 8 and whose sum is negative 9, so it's minus 1 and minus 8. And then, since these two things multiply to give 0, one of them has to be 0. And we get the two answers, x equals 1 or x equals 8. So that's by factoring. Some quadratic equations can't be factored. there are no two numbers whose product is positive 8, or two simple numbers whose product is 8 and whose sum is negative 40. When this happens, there are two main ways of answering it. One is called completing the square, and the other is called the quadratic formula. And I'm going to get back to this question in a minute, but I'm going to show you about these two methods using some other examples first. I guess the easiest quadratic question possible would be one that is just something like this: x squared equals a number. When that happens, x has to be the square root of 25, but it could be positive or negative, because negative times negative is positive. So this has two answers, plus or minus 5. 5 squared is 25, and negative 5 squared is also 25. Now, a question that looks similar would be something like this: x plus 3 squared equals 25. And it's almost the same thing. That means that x plus 3 has to be plus or minus 5. I'll even go like this first. So we're not done yet. As here, well, x was plus or minus 5. Here, 5 is not the answer to this question. X plus 3 has to equal 5, or x plus 3 has to equal negative 5. So if I subtract 3 from both sides, x has to be 2, or if I subtract 3 from both of these sides, x has to be negative 8. And those are the two answers for this question. Think about it. If you put 2 in for x, 2 plus 3 is 5, and then you square it to get 25. But if you put negative 8 in, negative 8 plus 3 is negative 5. Negative 5 squared is 25 also. Now, if you take x plus 3 and actually square it, if you actually take this expression, it turns into x squared plus 6x plus 9. Maybe you've learned the so-called FOIL technique of multiplying two binomials. Maybe you've learned that you can make a sort of square, and you make each side of the square like that, x plus 3, and this one is also x plus 3, and you can kind of see x squared, and this is the 3 squared, which is the 9. In general, when you multiply something like x plus or minus something squared, you end up with x squared plus 2 times whatever that a is, x, plus a squared. And when that happens, this thing is called a perfect square trinomial. So the way to recognize a perfect square trinomial, for instance, it's a perfect square trinomial if you take half of this x coefficient and you square it, and it turns into the constant term. If that happens, it's a perfect square trinomial, and it factors x squared. This would be true for minus also, because half of negative 6 squared is negative 3 squared, which is 9. So that would become x minus 3 squared. And just for reference, x squared plus 10x, what would have to go here so that this thing would be a perfect square trinomial? Well, it would have to be 25 because 10 over 2 squared does equal 25. So something is a perfect square trinomial if it's true that you take half of this number and square it, and it ends up being that number. And if not, then it's not a perfect square trinomial. So we could get a question like x squared plus 6x plus 9 equals 25. And if you recognize that 6 divided by 2 is 3, 3 squared is 9, then you can factor this to x plus 3 squared equals 25, which means that x plus 3 is either 5 or negative 5, which means if x plus 3 is 5, x equals 2 is one number that makes this equation true. And when x plus 3 is negative 5, which happens when x equals negative 8, makes this equation true also. Now, you may not get so lucky to get a perfect square trinomial on the left-hand side. What if instead my question said x squared plus 6x equals 16, or minus 16 equals 0? So this left side's not a perfect square. So a sneaky trick is to add 16 to both sides, like that, and then you say, okay, x squared plus 6x, if there were a 9 here on the right hand after the 6x, then this thing would be a perfect square trinomial on the left. So if I do plus 9, but I have to do it on both sides, now the left side is a perfect square trinomial and can be factored. And the right side, we're kind of lucky, the right side became a nice perfect square. And now we're back to that other question from before, where x equals 2 or x equals negative 8. But that question started as this. That process is called completing the square. That was when we put this 9 here and here in order to make the left-hand side into a perfect square. So that's called completing the square. Now, completing the square works even if the answer has irrational numbers. So here is a 40x plus 8 equals 0. So if you subtract 8 from both sides, you get x squared minus 40x, leave a little room, equals negative 8. Now, to complete the square, we take half of negative 40, divide by 2, and square it to get 400. I add 400 to both sides. That turned the left side into a perfect square trinomial, which can be factored to x minus 20 squared, and the right side became 392. Now 392 is not a perfect square. That's okay though. We can just go like this, just leave it as square root of 392. That's plus or minus, because whatever the square root of 392 is, if I square it, I get 392, but also the negative of it would also get me that, about 19. So 19 point something squared would get me 392, but negative 19 point something squared would also. And I can now say, so x minus 20 is the square root of 392, or x minus 20 is equal to negative square root of 392. So our answers are 20 plus the square root of 392, or if I add 20 to both sides of this equation, it would be 20 minus the square root of 392. Now maybe you don't like irrational numbers. So I'll tell you that 20 plus the square root of 392 is approximately 39.8. And 20 minus the square root of 392 is approximately 0.2. Now another example that's going to end up being important, and it's actually the first question. When I listed the 4 questions that we're building up to, there was a quadratic equation, a cubic with no x squared term, a cubic with all terms, and a 4th degree. Well, we're now ready. I'll call this equation number 1 that's going to come in handy. X squared minus 380 plus 2197 equals 0. If I do this, that's 380x, I mean. If I do this with the completing the square process, I would have to take half of negative 380, which is 190, and I'd have to square that, and I get plus 36100. I have to do that to the other side also. And this factors now to x minus 190 squared is equal to 33903, which means that x minus 190 is plus or minus the square root of 33903, which means x is going to be, if I add 190 to both sides, I can write both answers. And just for reference, if you're wondering, what are those? 190 plus root 33903 is about 374.1 approximately. And 190 minus square root of 33903 is about 5.9. So that's a little review of quadratics and completing the square. There is also, if you do completing the square with the equation ax squared plus bx plus c equals 0, and you divide both sides by a, and you go through this completing the square process, you would eventually end up with the famous quadratic formula. You don't really need the quadratic formula because completing the square always works. If there's a number in front that's not a 1 here, it's good to divide by that divide everything by that before you do the completing the square process. So the quadratic formula, some people like the quadratic formula better because it just is real quick and easy. Let me show you how that same question could have been done with the quadratic formula. So that question, which was x squared minus 380x plus 2197 equals 0. it would be x equals negative b, which is negative 380, plus or minus the square root. Now if you do negative b, if you do b squared minus 4 times a times c over 2, this turns into, eventually, 380 plus or minus the square root of 135,612 over 2. Now it turns out that this 135,612 because that's equal to 4 times 33903, and then you can bring this 4 out. Square root of 4 is 2, so 380 plus or minus 2 root 33903 over 2, and then you can divide both of the terms by 2, and you get 190 plus or minus square root of 33903, which is the same answer that we got in the completing the square process before. So with that, you get to the end of what most people do with algebra in high school as far as solving equations. You can solve any quadratic equation with the quadratic formula. Now when the exponent is bigger than 2, like suppose I have this is a 4th degree equation, so we haven't looked at these yet. This is our first one. We'll see, but this is not a hard one. If you have a situation where there's no x cubed term or x term, so you have x to the 4th and x squared and a constant, you could actually think of this as x squared squared minus 10x squared plus 9 equals 0. So it's a lot like if this was a 2 and this was a 1, I'm going to make a note. It's like u squared, I'm just going to call it another letter. It's like that. And just like this thing can be factored to u minus 9, u minus 1, this thing could be factored to x squared minus 9, x squared minus 1 equals 0. And then those two things individually, we can see what numbers make those things 0. And it turns out x squared equals 9, so x equals plus or minus 3. And for this one, x squared equals 1, so x equals plus or minus 1. So this 4th degree equation actually has 4 answers. But it's very unusual to not have like an x cubed or an x term. But if you do have this situation, there's an x to the 4th term, an x squared term, and a constant, you can solve it with factoring, or there could be situations where you even need to do the quadratic formula. We'll see some of those coming up. This trick of recognizing something as kind of being very similar, something with 3 terms being similar to a quadratic equation, or working the way a quadratic equation works, it also works for a question like this. So if you see 3 terms, and if you see this exponent is double this one, and the last term is a constant, you can do it the same way. So this is, I'm just going to say it's like u squared minus 9u plus 8 equals 0. Well, that would factor to u minus 8, u minus 1 equals 0. So this thing factors to x cubed minus 8, x cubed minus 1 equals 0, which means x cubed minus 8 equals 0, or x cubed equals 8, or x equals 2. Or x cubed minus 1 equals 0, x cubed equals 1, or x equals 1. Now a question like this with a exponent of 6 and 3 is going to come up eventually in a context for solving more complicated equations, but I just want to show you these numbers. This is related to that question I did before where I did x squared minus 380x plus 2197. So I'm just going to go like this. I'll call this x cubed squared minus 380x cubed plus 2197 equals 0. I'll just write down it's like u squared minus 380 u plus 2197. But that one doesn't factor. That one had an answer with the quadratic formula, or completing the square of 190 plus or minus the square root of 33903. And that happens here also, except it's not that x equals that, but x cubed, just like in this one, it was x cubed equals 8, not x equals 8. So this one is going to be x cubed equals 190 plus or minus the cubed square root of 33903. And you could put this down, save it for later, if this equation ever, comes up again. Those are the two answers. Oh, sorry. It's not finished yet because it's not x, it's x cubed. So finally you can take the cube root of both sides and you get a really unusual looking answer. Two answers really. I'm going to separate them out. Wondering, this complicated expression is about 7.2, and this complicated expression is about 1.8. Okay, so now we've seen quadratics and things that are like quadratics or that can be solved with quadratic formula. But let's start turning our attention now towards cubics. The easiest possible cubic would be something like that. Take the cube root of both sides, you get 2. It's not plus or minus 2, it's just 2. There's also some imaginary answers, but don't worry about those right now. But if your cubic has other terms in it, it can be pretty difficult. Unless you get lucky. Like in this cubic equation, if you factor an x squared out of the first two terms, and factor a negative 1 out of the third and fourth terms, you get lucky that these two things happen to match, because then I could factor those out. And then we can say that either x plus 2 equals 0 or x squared minus 1. This is called factor by grouping. And it's very unusual for it to actually work. But in this case it did. And we get 3 answers. But it's so unusual for factor by grouping to work that I'm not going to spend any more time on it. There are other times where a cubic equation has a rational root. For instance, you get an equation like x cubed minus x squared minus 3x minus 1 equals 0. Factor by grouping wouldn't work, but through some sort of trial and error, you might find that that this thing is divisible by x plus 1 and then you can say that x plus 1 equals 0 leads me to one of the answers, and the other two answers would come by doing the quadratic formula. After you set x squared minus 2x minus 1 equals 0, you get x equals 1 plus or minus the square root of 2. But again, that's pretty unusual. That would only work if it's factorable, and most cubics are not factorable. Okay, I think I'm going to make this end it as part 1. Basically, we got through all the review of the quadratics. Part 2 will be we'll start on the cubics.